Swayam Prabha. Digital India. Educated India.
We were looking at the fatigue fracture of the compressor blade of an aero engine, and while we were studying fatigue as well as fracture, what we were talking about or focusing our attention was on the mechanical stress raisers, particularly the machine marks left behind or notches or some faulty design of the machine element which would lead to stress raisers. However, if you look at this particular failure, you see that compared to the new high pressure compressor rotor blades, you see that the blade has been eaten away at the edges. At these two blades have been damaged because of being eaten away at the edges. So basically what it means is the blades have not been resistant to the incoming air and the dust particles, for example, which come with it. So these dust particles would eat away the blades purely because of their impact and abrasion that they cause, because the air is moving at a high speed as it gets into the engine, and then this compressor would this compressor blade would therefore be subjected to bombardment of these dust particles, and wherever it is the weakest, meaning wherever it is the thinnest, the cross section would be thinner towards the outer periphery, and that is where it has been eaten away preferentially. However, there is a point at which blade has fractured as well. So that brings us to a point whether the material composition was faulty, but no, the material composition is not faulty, because all chemical composition parameters lie well within the acceptable limits. So if you look at the specification, the fractured high pressure compressor rotor blade had chemical composition well within the range. So therefore there is no reason to believe that the material was deficient. But then if you look at the profile of the blade and the stress distribution and so on, so this if you look at the stress lines, this is where the crack originated, and apparently there is no reason why the crack should originate. So this means that in the absence of any mechanical stress raisers, which we have been talking about so much in case of ductile fracture, brittle fracture, fast fracture, fatigue, here you do not see any of these mechanical stress raisers. So then it means that the reason should be metallurgical in nature, meaning there are certain soft spots which are being left behind. So the material has not been made hard enough, the material is not equally hard everywhere, due to which at the edges it got eaten away faster. Then there is a soft spot over here, due to which the crack originated, and finally failure took place. And when you look at the fractography of or the different fracture surfaces, what you find is that there is a ductile fracture. So this is a final ruptured fracture, and here you have fatigue striations in the progressive crack propagation zone. But then by and large this also shows some good evidence of ductility, because this also shows some dimpled fracture, and further probing into the area where fracture or crack originated, one found a tight shallow crack on the convex surface in the vicinity of the crack origin. So, what it means is that already a tight shallow crack was present. What we mean by tight shallow crack is that the crack width, the crack length is very long, but then the radius of curvature is very sharp. So, basically it was a tightly closed crack. So, it was not something that had opened up significantly, and the radius of curvature at the two ends was very sharp. And if you look at further deeper into the structure, you look here. So, this is a very shallow crack which is visible at a very high levels of magnification. So, that is what brings us to the initial defect that was present in the material. So, it was not an external geometric defect, it was a defect which was born internally, and this internal defect then propagated and led to the failure. So, this crack propagated during the fatigue. So, as you know, during fatigue the transient softening takes place because of the reversal in the stress directions, loading unloading type of fatigue, and therefore, you have this kind of crack propagating incrementally. The crack propagates incrementally with every cycle, and then finally, there is a region of fast fracture where the final fracture zone is located. So, this is where you see the dimpled fracture in the final fracture zone, but then the whole story started here and it propagated incrementally with each additional fatigue cycle. So, now if I have to say what is the kind of life that I can expect from a product which I have made. So, for example, the product I have made is like a turbine blade which is subjected to fatigue loading, and this fatigue loading would cause incremental damage supposing there is a flaw in it, because we know that that material is never flawless, and therefore, if there is a flaw in it, it could be mechanical, it could be metallurgical, but then if there is a flaw present, it will incrementally propagate. Now, I have already said that if you do not allow the flaw to propagate, then you can rest assured that there is going to be no fracture. But in case of fatigue, what happens is that the state of stress or the state of loading is not monotonic in nature, it always reverses directions, and due to which the metal gets fatigued, and as a result the fatigue damage gets accumulated. So, fatigue damage is always cumulative in nature. So, fatigue damage keeps accumulating, and over many cycles of fatigue you have accumulated damage, and therefore, if you look at this fraction which is a part of the which is essentially the Miner's rule, Ni is the number of cycles subjected to under one stress condition, and a capital Ni is the fatigue life under those many that much amount of stress. So, Ni is the fatigue life in number of cycles at stress Si, whereas Ni is the actual number of cycles to which the body was subjected to, or the workpiece was subjected to at the stress Si. So, now when this quantity which characterizes the cumulative damage, okay, this quantity characterizes the cumulative damage in the system. So, as this quantity reaches a value of 1, then the damage is complete. So, if I have subjected, let us say this to 1000 cycles, okay, at stress Si, and the fatigue life at stress Si is, let us say 10,000 cycles, then I have accumulated 10% damage during my 1000 cycle schedule as far as the fatigue damage accumulation goes. Later on, I switch over the number of cycles, I switch over the stress to, let us say, double of Si or maybe a higher value of Si, and then the number of cycles to which it gets exposed to is also different. So, now there is another parameter meaning you will have here N1 upon N1, capital N1. Similarly, you will have N2 divided by capital N2, where N2 is a different value of stress N2 small n2 is a different value of number of cycles. So, capital N2 will be the fatigue life under stress S2 and small n2 will be the number of cycles to which the body has been subjected under stress S2. So, now you will therefore have N2 upon capital N2 getting added to this, because fatigue life is cumulative. So, small n1 upon capital N1 plus small n2 upon capital N2, and this way you keep on adding to the cumulative fatigue damage that would be introduced into the material as we subject it to different conditions in service. So, now when this when the addition becomes equal to 1, then you can be sure that there is no further life that is present in the material. So, now the Minor's rule assumes that the kind of damage that you cause is dependent on the stress. So, if you expose the material to higher levels of stress for longer durations of time, meaning for longer number of cycles, larger number of cycles, then the cumulative damage, the fatigue damage is more. If the number of cycles are few and the stress is also low, then the damage is that much less. So, basically the intensity of stress and the number of cycles at that particular stress determine the intensity of damage due to fatigue. So, since the damage is cumulative, the fatigue damage at different loading conditions for different cycles keeps on getting added, and when it becomes equal, when the addition becomes equal to 1, you say that the part is no longer usable. So, now when you apply this rule to partly utilized component, let us say I know the history through which the part has gone. So, now I know the number of cycles to which it has been exposed, the stress to which it has been exposed, the whole schedule is known. So, I can find out how many cycles, supposing I have another loading schedule in mind. So, I should be able to calculate as to how many cycles at that load will this component last. So, that will be based on Minor's rule, and I will demonstrate to you in the next slide how this is done. But then sometimes people make things a little easier or simpler. They assume critical damage to be same across all stress levels. So, what it means is that the material will withstand same number of cycles, or the critical damage will be the same irrespective of the stress. So, here in the Minor's rule what is assumed is that when the stress level increases, the critical damage occurs at a lower number of cycles, whereas here that is not the case. Critical damage to be same at all the stress levels. And so, what you do is that you have a sum of N1 into S1 upon capital N1 into S1 plus N2 into S2 divided by capital N2 into S2 plus small n3 into S3 divided by capital N3 into S3, and this way you have this ratio being added up. So, C represents the proportion of the cumulative damage at the damage to the critical value. So, when C equal to 1, failure occurs. So, the definition is the same as what it was here, but now that assumption is different. What you assumed here is that the critical damage is same across all stress levels. So, let us see what kind of difference it makes. Now, we have a situation where we have a rotating shaft which is subjected to bending moment, and then I have loaded it to certain number of stress, certain amount of stress to certain number of cycles. Okay. So, this is the actual number of cycles. So, if it is 1000 newtons, then the actual number of cycles is 5000 cycles. 800 newtons I have loaded it to up to 6000 cycles. At 600 newtons I have loaded to 10,000 cycles. 400 newtons remained for 1 lakh cycles. So, basically this it has been the loading schedule which I have had. Now, I want to find out what is the residual life, how long will the product last if I am going to load the material at 900 MPa. So, my idea is to load the material at 900 MPa. I do not know how much life it is going to have. Now, if I have tested, if I know that 900 MPa a fresh workpiece will last for 40,000 cycles. So, at 900 MPa I believe that a fresh workpiece will last for 40,000 cycles. Now, this workpiece has gone through use to significant number of cycles. So, naturally I cannot assume that to be new and say that okay, it will last for 40,000 cycles at 900 MPa. So, now I have to find out how many cycles would be possible at 900 MPa. So, for that what I do is that I have the stress amplitude and the actual number of cycles. So, 5000 into 1000, right. So, not 5000 into 1000, I have actual numbers of 5000 divided by cycles up to failure. So, cycles up to failure at 1000 MPa is 10,000. So, 5000 divided by 10,000 is 0.5. So, 50% of the total cumulative damage has already been done by this stress amplitude here. Then I switch over to 800 MPa as the stress and subject it to 6000 number of cycles, which means that 6000 divided by 50,000, because now at 800 MPa the cycles to failure are 50,000. So, naturally just 12% of the total fatigue damage has been introduced by 800 MPa and 6000 cycles. I have 600 MPa and 10,000 cycles, and the damage that has been introduced by these two is quite insignificant at just 3.33%, and therefore, a very small amount of damage. And if you look at 400 MPa, which is much less than 600, the damage is even less at just 1%. So, effectively what I find is that over these cycles at these 4 different stresses, I have consumed 66.33% of the life. So, the total damage that has accumulated is 66.33%, which means that the available life is 33.7% roughly. 33.7% is available, and so what I do is that I have this 40,000 for at 900 MPa. So, of these 33.7% is available, and therefore, I get 13,467 number of cycles which are available at 900 MPa. So, now this is based on the Minor's rule. Based on the Minor's rule, the fraction of the total fatigue life for a fresh sample or for a fresh product at 900 MPa has been let us say given at 40,000 number of cycles, and given just the 33% life that is available, because already the fraction of life consumed is 66.3%, then what I can possibly get is very safely get. So, what it means is I can get it without say any kind of breakage or any kind of failure. So, I get 13,466 cycles at 900 MPa. Now, if you look at the critical damage being same across all stress levels, then I get a completely different picture. So, the Ni so this is Ni small ni into Si, right, divided by, so this is small ni into Si divided by capital Ni into Si. So, this is capital Ni into Si. So, that is what we have calculated. And now what we have done is that you have taken the cumulative of these two. Okay. So, the total of Ni into Si is just so this is total Ni into Si numerical I mean numerator total, denominator total, and then we find that just 1.3% of the life is consumed. So, it all depends upon how you have calculated, what assumption you have used. Usually Minor's rule is used because it is more logical, one would expect more damage to get accumulated, and therefore one would accept cumulative damage taking place. Now, these are all linear additions, the cumulative damage is being linearly added under different situations. So, these the damage which has taken place under different situations of stress and number of cycles is being linearly added, which gives us a perfectly acceptable estimate of the residual life. So, that is why we accept it, but normally there are many interacting factors which would affect the cumulative damage, the life, etc. But then to keep the formula simple, to keep the analysis simple, we have a linear addition of these two, these damage accumulated under different conditions, and determine the residual life. Anyway, it is an estimate. We are always going to be lower than that, because we are not going to exhaust all these 13,466 cycles, but it gives me a ballpark figure as to what is the fatigue life going to be. Now, if you look at this stress amplitude versus cycles to failure curve, you find that here there is a greater stress, and so the stress increases and the corresponding number of cycles to failure decrease. So, this part is heavily dependent upon the stress, because higher is the stress, it has got a significant effect on the number of cycles to failure. On the other hand, at this stress there is no effect. Okay, the number of cycles to failure can be 10 to the power 7, 8, 9, 10, it does not fail at all. So, what it means is that the material is able to endure, the fatigue damage for infinite period of time. So, this will happen when the amplitude of stress is very low, right, when the amplitude of stress is very low, and then the crack or the defect inside does not propagate. So, the stress is too low to get the defect to propagate, in which case we can always get infinite number of cycles as the predicted life. And so, normally what people do is, once you have people have standardized 10 to the power 7 cycles as the an estimate for fatigue life. So, as the estimate for for determining the endurance strength or fatigue limit. So, the stress at which the workpiece can withstand 10 to the power 7 cycles without any kind of failure is given as the endurance strength. So, you can be sure that the material will endure that much amount of stress forever. So, the crack will not propagate, the defects inside will not grow into cracks, and the defects will not propagate, they will not result in any kind of fracture, and so the fatigue life can be taken as infinite, because the defects would remain inside without getting enlarged any further. So, that brings us to another issue which is again related with crack propagation and so on. How does the crack propagate with number of cycles? So, I told you that you see striations, you see evidence that the crack has propagated by a very small distance and in every cycle. So, the damage which has been done by each cycle is recorded in the form of striations on the surface of the fracture. And then once the cross section left is relatively small, then you have fast fracture, because now there is nothing to arrest rapid propagation of the crack. So, that is what we call as fast fracture, and that is what we saw in one of the pictures which we were studying earlier, for example here. So, here you have initiation, fatigue crack propagation, and region of fast fracture. So, that is what we are able to we will be able to see now in case of this. So, the crack growth rate is given by dA by dN. So, the dA by dN. So, A is the length of the crack, N is the number of cycles to fatigue, and here you see that the rate of change of crack is not equal everywhere. Okay, it is not the same everywhere. You could have a surface crack, or you could have surface, when I say surface crack, it means surface defect, or you can have an internal defect. Now, when you have the stress intensity factor, so this stress intensity factor is basically intensification of the stress due to presence of a discontinuity. So, sigma m by sigma naught. Sigma naught is the average stress based on the entire cross sectional area being assumed to take equal amount of load, or the stress distribution being constant over the entire cross section. So, that is sigma naught, and sigma m is the actual stress felt at a discontinuity. So, you have either a step or an internal flaw, or at the edge of the flaw you have very sharp radius. So, there you will find the stress is not equal to the average stress, it is far higher than the average stress. So, that is what we call as the stress intensification, right. So, up to a certain degree of stress intensification, let us say less than 0.2, there is no crack growth at all. So, within this region there is no crack growth at all, because the stress intensification is so low that there is no chance of crack propagating. So, any defect inside in the form of a discontinuity or a crack or anything else is not going to propagate. So, it is safe. But then as the stress intensity increases, as the stress intensity factor goes up, then you have a very slow crack growth. The crack growth is extremely small. Then as the stress intensity increases, your crack growth rate acquires this power law behavior. So, you have dA by dN, the rate of growth of the crack is proportional to is in fact not directly proportional, but it is related in a non-linear manner with a change in the value of k. So, we have seen that k can change. So, delta k can be the outcome of either stress sigma changing or the crack length changing, because k is defined as sigma root of pi a, right, sigma root of pi a into this factor of course, but these factors are constant depending on where the flaw is located or flaw has been assumed to be located. So, what we do is that the delta k can be attributed to either delta sigma or to delta a. Now, as the crack is growing, naturally even when the sigma is small, the delta k can occur, can change because of the growth in the crack length. So, here there is no crack growth, there is no as sigma changes, then only the k will change. So, as you go on increasing the delta k value, then the crack starts growing. Now, beyond this point the crack, there is a slow crack growth. So, as a result the stress intensity factor delta k now changes with the increasing length of the crack or increasing crack growth. So, as a result the crack growth rate also increases, because now you have delta k being determined by a change in the length of the crack. The crack is growing, but slowly, it is growing slowly, definitely it grows slowly, but it does grow, right. Now, after a while, after the stress intensification continues to increase, so as the stress intensity grows, then there is a rapid or let us say power law type of crack growth, more rapid crack growth. So, as you see the slope over here, there is a power law being followed. So, here you have the C into delta k to the power n as the fast crack growth, and then beyond a certain value of delta k, because now as the crack grows delta k is changing. So, sigma root of pi a is our value of k. So, now as the value of a keeps on changing, you will have a change in value of k. So, naturally delta k with every crack advancement will result in a new value of the rate of propagation of the crack. So, dA by dN defines how much is going to be the change in the length of the crack per unit cycle, and that is what the beach marks or the striations on the surface of the fracture will indicate to you. So, how much has it advanced in one cycle. So, now for example, for this steel C equal to 162 into 10 to the power 1.62 into 10 to the power minus 12 and n equal to 3.2. So, k equal to this expression, and one can calculate different in different regimes how fast the crack is going to propagate, because now you know the these constants here, right, you know the n here, and so corresponding to a value of delta k you will get a corresponding value of delta n, dA by dN. So, the as the crack grows more rapidly over here. So, you see there is a slow crack growth here and there is a much more rapid crack growth here. The rate at which delta k will increase, meaning the delta k will shift to the right, continues to increase, and then here it becomes extremely high. So, now we take up a small problem which you can solve at home, and then we will also give out the solution to that. A high strength steel plate which has a plane strain fracture toughness of 80 MPa meter raised to 0.5 is alternately loaded in tension to 500 MPa and compression to 60 MPa. So, now you see that the loading is not symmetric between tension and compression. It is more in the tension region, it is less in the compression region, but nevertheless it does get into the compressive regime. So, the plate is to survive for 10 years. So, the life of the plate you expect is 10 years, and it is being subjected to this kind of fatigue 500 MPa and in tension and 60 MPa in compression. So, the stress is applied every 5 minutes. So, you have 500 MPa and then the new stress of 60 MPa is applied. So, it goes to 60 MPa after 5 minutes, again it comes back to 500 MPa in the next 5 minutes, then it again goes down. So, this way the stress is applied every 5 minutes, and so the question is how do we design the manufacturing and testing procedures that guarantees that the component will serve as intended, meaning the component will have the intended life of 10 years at the stresses it is going to be subjected to. So, namely 500 MPa in tension and 60 MPa in compression. So, with this we summarize that fatigue damage is always cumulative, it cannot be reversed in any case. Fatigue damage can occur despite no obvious mechanical stress raisers, that is because you can have metallurgical defects as well. So, although the geometric defects can be eliminated by conscious design effort, the metallurgical damage or metallurgical deficiencies can result in soft spots remaining behind, meaning the material being weak at different locations, which results or which nucleates in a crack, because even in the absence of mechanical stress raisers, your stress magnitude that is acting on the workpiece is going to cause a greater amount of deformation in the relatively weak zone, and as a result it will therefore have much less ductility, or it will exhaust its ductility very rapidly, and therefore the damage will keep on accumulating. So, now with the accumulated fatigue damage, with the ductility getting exhausted with every fatigue cycle, there will be a crack nucleated and finally it will propagate. So, there will be a decrease in the stiffness of the product, because now as the crack propagates inwards, the damage is being done progressively. There will be continuous decrease in the stiffness of the product. Low cycle fatigue involves plastic deformation due to the higher stress levels, while high cycle fatigue involves elastic deformation only. So, I had shown you this curve. I think we observed this, that here for example, you have very high stress, and correspondingly you have much lower number of cycles to failure. Now, as the so here the deformation is plastic in nature, there is permanent deformation, you have crossed the yield point, and as you go down you go at some point below the yield point. So, the endurance limit would be below the yield point. So, while low cycle fatigue, meaning fatigue at which the life is relatively small, the number of cycles the component survives is very small. So, in that case this is called as low cycle fatigue. The plastic deformation is part and parcel of low cycle fatigue. The low life, that is smaller amount of life, is also, or smaller duration of life is also a part of the result of the low cycle result of high stress and plastic deformation taking place. The ductility getting exhausted and then the crack getting nucleated and the crack propagating throughout the entire mass of material. Whereas here this you are in the elastic regime, here, so there is no permanent deformation. So, what is happening here is that there is only change in the sign, there is only change in the direction of deformation in case you have both tensile as well as compressive stresses. And so, we have a fatigue limit which is much lower than the yield point of the material. But then here it will not only withstand the stress forever under monotonic loading, it will also withstand the stress forever, meaning more than 10 to the power 7 cycles in fatigue loading as well. So, with this we come to the conclusion of this lecture. So, here what we see is that different amount of fracture toughness that the material has also plays a role in fatigue, because for the fatigue crack to propagate, the toughness of the material should be sufficiently high. And so, you have engineering alloys where the fatigue toughness is relatively high, and then there is medium with engineering polymers, porous ceramics having very poor level of fatigue toughness, and polymer foams, of course, because of inherently present defects in the form of holes, because polymer is essentially a polymer foam is a essential fluffy entity, which means that it already has got plenty of blowholes or something like that, basically, which can be considered as defects in case of fatigue. So, with this we come to the conclusion of the topic on fatigue and fracture. You have got an exposure to fatigue and fracture, but now we will come to the to another discussion on what is called as heat treatment, because we saw during the lecture that in spite of not having stress razors, we had a spot that had remained soft in the material. Normally what happens is you add alloying elements, you add different kinds of you make different kinds of additions to the material to generate certain property that you want. And with these materials generating different phases in the so these elements generating phases in the material, then you have the desired strength, the strength distribution is as per your desire, and therefore you do not have any fatigue failure or stress concentration or stress razors being generated. But at many spots or many points, for example, you might have held the workpiece at that point using a tong or something else, due to which the tong did not leave any impression, tong did not leave any mechanical impression on it, but what the tong did was it would have changed the history of heating and altered the heating rate, altered the cooling rate, and thereby changed the microstructure. So, basically the microstructure everywhere else was probably homogeneous, whereas here the microstructure was not the same as microstructure elsewhere, and that is one reason why we come to the topic of heat treatments. Now, you have added certain amount of materials which get organized into phases. Each phase has its own strength. So, now you have a congregation or you have an aggregate of a matrix which has got certain alloying elements, and there are a number of phases which are, say, intermetallic phases of different structures which are present in the material. Now, when the crystal structure changes, the strength of that phase changes, right. Similarly, the all physical properties of the phase are completely different as compared to the physical properties of another phase. So, naturally, what you have done is you have reorganized these elements. For instance, if you take austenite, so all the alloying elements are in a single phase called austenite, which is a phase centered cubic structure. Now, if you cool it down, then this structure gets generates or precipitates out the ferrite and cementite, or ferrite and pearlite, depending on what the carbon composition is, depending upon the chemical nature of the material is. So, what I am saying is that in the context of steel, for example, as you heat the material to austenite, you have just a single phase, everything is in the dissolved form, all alloying elements are in the single phase. But later on these they get reorganized into different crystal structures like ferrite, pearlite and so on, and therefore, what you have is a completely different mechanical strength and a different mechanical property. So, heat treatments enable us to reorganize the alloying elements in the material, so that you either have them present homogeneously all over, or you might reorganize them into different kinds of phases. You could reorganize them into different intermetallic compounds. So, it all depends upon how you what you are going to do, or in what is the schedule of heat treatment, meaning how you are going to heat, for how long you are going to heat, what temperature is going to be maintained. So, these are all the questions which need to be answered when you say that you are going to reorganize the chemical composition of the material of the alloying elements inside the material, right. Okay. So, you have homogenization as one of the heat treatments, where you would like the entire set of alloying elements to get homogenized all over the geometry of the workpiece. So, the first treatment that is given is homogenization, because there is a possibility that during the course of previous processing there would have been so called segregation or non-uniform distribution of elements in the material. Now, this is typically so when the previous step has been a casting process. For example, if you have just poured out hot metal into a mold, and then by the time it solidifies, you have different phases formed there also, but during the course of solidification you do not have uniform distribution of alloying elements everywhere. So, in certain regions, we will see now how this happens, but then if you look at any of the phase diagrams which we have already studied, there you will find that as the material cools, the distribution of the alloying elements keeps on changing. So, let us say the material cools from liquid phase to just below the liquidus. Then what you will have is a combination of solid and liquid. Now, the solid which has resulted will not have the same chemical composition as the liquid. So, now what will happen is that the liquid will get either richer or leaner in the solvent, and you will have the crystals or the layers which become solid with a different chemical composition, because now the different chemical composition of the liquid changes, because what is solidifying is not the mean chemical composition which you had intended. So, naturally, the first crystals or first solids which appear just below the liquidus would be different in terms of chemical composition compared to your intended composition. So, if you have to bring everything to the intended chemical composition, you need to homogenize the material by heating it to a sufficiently high temperature and leaving it for a very long time, so that the diffusion of these atoms takes place, and therefore, it becomes a uniform distribution of the alloying elements. Another variety of heat treatment is so called annealing, where you heat the material to a very high temperature, and now what you are doing is cooling it at a very slow rate. So, in homogenization what you did was you held the material for a very long time at high temperature allowed the alloying elements to diffuse so that the chemical composition becomes uniform all over. Now, if you look at the annealing process, it is a process where the material is heated for a very long time, where the temperature becomes equal. So, the idea here is not to homogenize the chemical composition, but to result in either recovery, recrystallization or grain growth. So, recovery means you relieve all residual stresses or the stresses which might have been induced in the material during the course of manufacturing. So, how do you do stress relief annealing? So, when you heat the material to a high temperature, you are bringing now the yield point of the material. Now, the level of these residual stresses can be higher than the yield point. So, which means that the residual stress gets the material into the plastic deformation range, because now the stress level, the residual stress level is higher than the yield strength of the material. Why? Because you have heated the material and brought down the yield strength. So, naturally there is small amount of plastic deformation taking place, and so the residual stress that was present gets relieved because it has been dissipated in generating some amount of local plastic deformation. So, you do not see it on a global scale, you do not see it at a very macroscopic scale, but then internally the stresses get relieved in the material. Of course, the material has to be fixtured and it has to be put in the right orientation. So, for stress relief you need to put it in a proper location, orientation, etc. Then you go on heating it even further, you keep it for a longer period of time, it can even recrystallize, meaning the older grains can be replaced by the newer grains. And usually what people do is, when you anneal the material to high temperature and long durations of time, then it is possible to generate what is called as a fine grain size. So, for grain refinement people use this recrystallization annealing, and then after that if you still keep the material long enough, then the grain growth starts. So, the number of the grains you have continue growing, the size keeps on increasing, and this grain growth is purely because of diffusion of atoms becoming easier and easier as you keep the material in the furnace, keep it at a high temperature for a long period durations of time. So, annealing is done with three purposes. One is to just dissipate the internal stresses by causing local plastic deformations. Then you have recrystallization taking place, meaning the old grains are replaced by the newer ones, and then the grain growth takes place. You do not want to the grains to grow indefinitely. So, you do not want, let us say, too fine grains, you do not want too coarse grains. So, the grain size that you want can be adjusted during the annealing process. So, what people do is, people often work the material using thermomechanical treatment, meaning they roll the material or forge the material, generate large amount of dislocation density in the material, and then they put it for annealing. So, there what happens is that when the dislocation density is very high, then there are large number of nuclei for new crystals to form. So, now if I have the grains of certain size and I have deformed them to large amount of strain, then I have plenty of dislocations inside the grain, and these dislocation or a high dislocation density or dislocation clusters, dense clusters inside the grain will serve as nucleation sites for the growth of new grains. So, that is why my recrystallization gets triggered from inside the grain, and so the size of the grain, so the size of the initial grain will get split into a number of smaller grains, and that is how we get recrystallization annealing. And then if you want, if you feel that okay, the grain size is too fine, I need a slightly bigger grain size, then I can grow the grains to the size I desire. So, then you have what is called a normalizing. Here what you do is you again heat the material to relatively high temperature and then leave it in the air. So, normalizing is basically air cooling. So, it all depends on the ambient temperature of air. So, if the ambient temperature of the air is as per summer, you will have one rate of cooling, in winter you will have another rate of cooling. So, if the climate is extreme, then you can have significantly different cooling rates in normalizing condition, because in winter it will cool faster, in summer it will cool much slower. Then there are different heat treatments which generate the kind of microstructure you want to generate the strength. Again, we are reorganizing the elements. So, what we do is that we initially get all the alloying elements into solution, solid solution, meaning there is single phase. So, you heat the material, let us say to an austenitic type of phase, for example, or to let us say a solid solution of alloying elements in aluminum. So, that is called as that is precisely why it is called as solutionizing. So, now if you put all these alloying elements into a solution and then you quench it, when you do quenching, there is no time for diffusion of these elements, plus the temperature decreases very rapidly, and therefore, the driving force for diffusion is lost. So, the alloying elements which are sitting in the solution continue to remain in the solution. So, what happens is, if the alloying elements have got dissolved in the single phase in the solid solution, they have no chance of forming any other phases. So, there is a single phase which has all the alloying elements residing in it. So, that is what happens when you quench the material, you do not let the diffusion take place. And then what you do is, again you want to reorganize this alloying elements. You are not happy with the strength you are getting when you hold the materials in a solid solution in a single phase. So, by solutionizing, the alloying elements are the same, but they are in a solution, they are in a single phase. What you want is something else, you want a harder material. Solutionizing does not create hardness beyond a point. Solutionizing has got great limitations in terms of the hardness that can possibly be obtained. So, what you do is that you heat it in a controlled manner. So, heat it at a relatively lower temperatures for a controlled period of time, so that you allow controlled amount of diffusion to take place and for certain phases to form. So, you know which phases are favorable to give you greater hardening, greater strength. So, you have that heating rate, that heating time, okay, holding time at the so called temperature at which these intermetallic precipitates would form and then get precipitated all over the material. Now, the advantage here is that if you have had a large number of dislocation density, or if you have worked the material a priori, then the sites at which these precipitates will form will be much larger. So, since the alloying elements are the same, the quantity is the same, but now it has to be dispersed over larger number of locations, then you have very fine precipitates being precipitated at a given location. So, if you have worked the material, if the dislocation density is higher, defect density is higher, dislocation clusters form, then the precipitates would be finer and they will precipitate at larger number of locations. So, this is called as aging, and when this aging takes place, these precipitates are relatively hard particles which would refuse to deform, and again these precipitates are coherent or semi-coherent and non-coherent type of precipitates, and depending on the crystal structure, the extent of match between the matrix material and this precipitate will be determined, and this mismatch also adds or contributes to the strength. And so, now you have a precipitate which has come out, the precipitate is harder, usually it is harder, it has got much greater mechanical properties, and this precipitate is something that cannot deform very easily, the crack cannot pass through it very easily, the crack may circumvent it. So, if the precipitate has got very good interface with the matrix material, then even that circumventing becomes difficult, and that is how you find that the material behaves much harder. So, the material does not let the dislocations move, they get held up at the interface with the precipitate. The stress on the precipitate keeps getting piled up because it is blocking the dislocations, and then the precipitate, being a hard material, being a strong material, does not either move, it does not get deformed, it does not get broken, right. So, it has got very high strength and it can tolerate large number of dislocations piling up against itself, and therefore, it becomes increasingly difficult for the dislocations to move, and that is what we see on a macroscopic scale as hardness getting increased. So, when I had solutionized the material, everything was in solution, the same set of alloying elements were uniformly distributed in a solution, but now when I got them to precipitate as intermetallic compounds, then I got a higher hardness, because these intermetallic compounds are harder than the matrix, and they are the ones which impart hardness or resistance to plastic deformation through the process of aging. So, there are plenty of heat treatments in steel which we will see soon. Now, you might not want to get maximum hardness all over the component. For example, you take a gear. Now, gear contacts the tooth of another gear, the tooth of one gear contacts the tooth of another gear on its surface. So, now the load transmission takes place at the surface, the one gear tooth slides relative to the other gear tooth, there is friction, there is a tendency to wear, because when there is friction and when the contact pressures are relatively high while transmitting torque, you have tendency to wear out, you have a tendency to get deformed, because under the load the gear geometry can change temporarily. So, there are basically lots of issues that can arise due to high load being generated or high load being felt at the point of contact between two gear teeth. So, now what we need to do is we need to make the surface hard, because what happens is, supposing there is a crack at the surface or the root or there is some stress concentration taking place, or for some reason there is a crack, then it should not propagate rapidly, because if I harden the material throughout, then I am losing in terms of the fracture toughness, because once the strength increases, the ductility decreases. Now, when I make the entire bulk of the material strong, I am paying in terms of reduced fracture toughness, reduced ductility. So, what it means is that if the crack were to indeed originate, then the plastic zone formed at the tip of the crack is going to be extremely small. It is going to be capable of absorbing a very small amount of energy. Naturally, the capability of arresting the crack will be very poor if the entire hardness of the entire workpiece is increased. So, the bulk hardness is not what I am interested in. What I am interested in is surface hardness, so that the crack does not propagate. If it goes into the interior, the crack does not get initiated because the surface is hard. So, that is why I have some surface hardening treatments where I can selectively change the chemical composition of the surface and generate phases of higher hardness. So, what I do is that on the surface I increase the say carbon, for instance, so that now on the surface I have got greater carbon content, in the interior I have got much lesser carbon content. So, for example, in the interior I might have just 0.2 to 0.3% carbon, but on the surface I might have 0.8 to 0.9% of carbon, as a result of which I will be getting a much better structure to withstand the wear and tear that we experience when the gears are operating. Same is the case with many applications where you do not want the crack to originate at the surface, like in a rotating bending type of fatigue. For example, railway axles undergo rotating bending type of fatigue damage. So, if the surface of the axle is hard enough, then you will not find you will not get to start with, the originating of the crack itself will be a little difficult. And so, during the process of heat treatment, what you will do is you will harden the surface selectively. We will see what how we can harden the surface selectively, but then having hardened it selectively, the deformation of the surface subjected to large bending strains or large bending stresses, not strains, large bending stresses, you will have very small strains being created, because now the material is stronger at the surface. So, naturally the strains created will be that much smaller, and therefore, the kind of damage it will accumulate will be that much lower. So, that is why we have case hardening or surface hardening type of treatments which are available for different materials. So, heat treatments can never be delinked from the phase diagram. So, if you look at the different temperatures in the iron carbon diagram, you have the melting point at around 1540 degrees centigrade, and then as the material cools down, depending on the percentage of carbon, you will get different kinds of microstructures. For example, in this case, if it cools from this particular point, let us say this is the chemical composition of certain percentage of carbon. As it cools down, you have liquid plus austenite getting formed. This gamma refers to austenite. So, slowly it cools, and then so this is the liquidus line, this is the solidus line, and then it has cooled below the solidus. So, it becomes entirely gamma, and so this is the austenite phase. It is a single phase. Normally what people do is, if they want to deform the material, if you want to generate a large dislocation density in the material, they heat it to the gamma phase, that is a single phase, and then they deform the material. So, you do not have to go to very high temperatures, you can go right up to here, for example. So, the temperatures are can be relatively smaller at 800 degrees centigrade or so. You can heat the material to austenitizing range, meaning to austenite temperature, get a single phase and deform the material. So, here it is not very strong, since you want to deform the material, you do not need it to be very strong either, but then in service you need it to be strong. So, naturally what you do is that from austenite you tend to deform it very rapidly to what you call as the martensite. Now, this is based on slow very slow cooling rate, but formation of martensite happens at a much faster cooling rate. So, you will not see any martensite over here, but then if you were to adopt very slow cooling rates, then you will get different kinds of microstructures depending on how the material has been cooled, at what cooling rate it has been brought to the room temperature. So, we will see more on heat treatments in the next lecture. Thank you very much.